In the last few videos, I've been making minor changes and upgrades to the robot arm and its software. Some of those changes, like the gripper, were successful. Most of those changes, however, were failures. In this video, I'll be changing that by revisiting the mechanical design of the robot and fixing most of the issues I've run into in the previous videos. I'll also be giving the electronics a much needed makeover, courtesy of this video's sponsor, PCBWay. PCBWay offers PCB manufacturing and assembly. You can get 10 two-layer boards for as low as $5, and new PCBWay members get a $5 coupon for their first order. That basically means you can get 10 two-layer PCB boards for free. They also offer a bunch of other services such as 3D printing, CNC machining, injection molding, and sheet metal fabrication. To learn more, you can visit PCBWay.com. The link can be found in the description down below. Thanks again to PCBWay for sponsoring this video. And without further ado, let's get started. I've been working on the robot arm for quite some time now. The first video was published on July 9th, 2021. There have been quite a few issues that popped up during this build, causing me a ton of headaches and frustration. On the mechanical side of things, I was having issues with the belt tension for the lower joints. It was causing me to miss steps during movement, and in some extreme cases, even caused the robot arm to crash into things or itself. Admittedly, I knew these issues existed and I kinda just swept them under the rug in favor of making progress. Most of these issues were easy to fix, just time consuming to do so. So I moved on to the software trying to implement things like inverse kinematics, joint interpolation, motion profiles, etc., hoping that it would work well enough so I didn't have to fix the mechanical problems I was having. It wasn't until recently when I was working on debugging the software that I realized nothing I could code would fix the underlying issues this robot has. So I decided to take it back to the drawing board and work out a way to fix these issues. Joint 3 is the main joint that was giving me issues while I was trying to work on the software. At first, it would just be some missed steps that caused the position error to grow the more it moved. Eventually, the joint couldn't hold its position at all and would collapse under its own weight like it did when I first assembled the robot. Upon taking the lower limb apart, I discovered that the mount for the stepper motor was severely bent and warped. I'm not entirely sure if this is because of the mechanical stress on the stepper, the heat produced by the stepper, or a combination of both. It could also be the fact that I've crashed the arm quite a few times during testing as well. There's also some loose fibers everywhere from the timing belts rubbing against things on the inside. Since I have to reprint this part anyway, I figured why not take the time to redesign it and fix those issues. For the redesign, I decided to forego the adjustable tension mount for the stepper motor and just mount it at the exact center distance I calculated for this belt and pulley combination. I also made the mount a bit thicker and merged it into a single plate on one side of the clamshell design. I then added a press fit holder for the bearings to keep the shaft aligned and remove some unnecessary material from certain places. To help with tensioning the second stage of this joint drive, I redesigned the belt tensioner to use a sliding mount for the bearings that allows me to adjust the tension by tightening an M3 screw. To keep the M3 screw in place, I picked up some of those square M3 nuts and added a captive nut slot to the design. My first test prints for the new design were promising. The motor fits perfectly on the mount and the belt seems sufficiently tensioned thanks to the increased center distance. I had to reprint the clamshell cover since I forgot to make space for the motor mount, which stopped it from closing around the other side. But once I had the correct prints and assembled everything together, I was amazed at how sturdy and rigid the new design was. There was very little backlash this time, and when back driving the joint, I didn't get any unpleasant noises or rattles like I did before. Joint 2's issues were pretty much identical to that of Joint 3, mainly due to them being driven the exact same way. The biggest issue I wanted to fix for Joint 2 was the lack of support for the motor shaft. Since I'm using a rigid shaft coupling to attach the motor to the pulley, this leaves the smaller shaft at risk of becoming bent and warped over time due to mechanical stress. I've started to notice this more and more during operation as the shaft started to rotate off-center. Upon further inspection, I also noticed the set screws on the coupling were coming loose, likely due to vibrations during movement. To fix those issues, I've added a bearing at the end of the shaft to hold it in place and keep things centered. I also made the same changes I did for Joint 3 to improve the belt tension and hopefully reduce the number of missed steps. There was also an issue with the pivot point for this joint that I didn't realize existed until I started to take it apart. In the design for Joint 2, there actually isn't anything holding the body in place mechanically. It kinda just sat in between the two bearings, and because the outer parts were stationary, it physically couldn't move. This meant that there was a ton of slop in this joint, causing the arm to slightly move back and forth sideways during runtime. To fix this, I redesigned the body of J2 by moving the bearings to the opposite side and using another printed piece as a bearing cap to hold it in place. After printing and assembling this joint, I noticed the same improvements that I had observed with joint 3, along with having barely any sideways movement on the joint now. The last major redesign was for the base of the robot arm. Right now, to mount the robot to a flat surface, you need to screw in the base from the inside during assembly. This isn't a good idea at all, since it would require me to take the robot apart each time I will want to adjust its placement. To fix that, I added a square flange to the base with mounting holes for 4 M8 bolts to keep the robot in place. I also decided to redo the wooden base of the robot in order to add more space for the wiring, connectors, and eventually some electronics. I picked up some 1/4 inch pieces of plywood from Home Depot and glued them together to make one 3/4 inch piece. It was actually cheaper to do this rather than to buy a 3/4 inch piece directly. I cut the board down to size and used a paper template to mark and drill the hole locations for the robot arm to be mounted to. I also added 2 thin strips of wood to each side in order to keep the board elevated and make space for the M8 bolt heads underneath. Since I changed the design of the robot's base, that meant I also needed to redesign and reprint a new mount for J1's motor. The new mount now contains a small space to allow for the sensor wires to pass throughout the back. I mounted the new base onto plywood and began reassembling the entire robot, taking special care to route the wires with enough slack for the arm to have a full range of motion. With the mechanical issues out of the way and my thirst for more problems to fix at an all-time high, I set my sights on the electronics. I mean, just look at it. While there may not be anything functionally wrong with the electronics, there's still a handful of things that could be improved. The biggest thing is the organization and cable management. So to fix that, we'll be putting everything into this plastic enclosure. The enclosure will house the stepper motor drivers, power supply, control board, emergency stop button, and anything else I decide to add to the robot later on, like a Raspberry Pi or other single board computer to run more complex software for the robot. For a more modular and cable managed robot, I'll be using these GX16 4-pin connectors for the robot motors and these 6-pin connectors for the sensors. I'll cut a space for a connector panel into the enclosure and wire everything up on the inside. That way it'll be easier to take apart the robot without having to take apart the electronics too. On the base of the robot, I'll be adding a smaller 3D printed enclosure where all of the wires will go into and be wired up to the GX16 connectors. For the cables of the robot, I purchased some 22 gauge 6 conductor wire and 20 gauge 4 conductor wire. I'll only cut about 5 feet for each cable. I don't want the cables to be too long, especially for the I2C sensors, since that may introduce some noise into the signals. Unfortunately, I'll have to wait until everything is wired together to see if there are any issues with noise. The control board will also be getting a small upgrade thanks to the sponsor of this video, PCBWay. On the previous control board, I had to remove my 5-volt regulator from the board since it kept overheating and shutting off under load. Rather than making space for a larger heat sink or adding a cooling fan, I decided to just remove it from the design altogether and add an input for an external 5-volt supply instead. I picked up this step-down 5-volt regulator from Amazon that could be powered from the same 24-volt supply as the motors and end stops. The soldering and assembly for this control board is basically the same as the previous one, so if you want more details about that whole process along with a more in-depth breakdown about how everything works, you should check out part 3 of this series for more on that. With the new control board assembled, which by the way, looks amazing. Great job as always, PCBWay. I made sure to test it out with the current setup first to make sure everything worked, and to my surprise, it did. I expected something to go wrong, but it didn't. I can't help but feel like I'm using up all my good luck early on and something is going to go wrong at the end. But oh well, time to work on the enclosure. For the enclosure, I'll be mounting all of the crucial electronics to the inside panel using some screws I picked up from Home Depot. But before I start mounting things in place, I need to make sure there's enough clearance for the connectors and other components that are going to need cutouts in the enclosure. Once I have a decent idea of how things are going to be laid out, I use a combination of paper templates and 3D printed pieces to mark all of the necessary hole locations and cuts I need to make. I also came up with this really simple way to mark holes for the power supply by driving the screws into the PSU and putting whiteout on the screw heads. Then all I need to do is place it where I want it, and the screw locations will be marked with whiteout in the enclosure. With all the necessary components installed now, all that's left is to wire everything together. I wired everything together except for the stepper motor connectors. I want to test out the sensors and make sure all that's working before I add the motors into the mix. On the robot's platform, I also wired up all of those connectors according to this wiring diagram I made so that I don't mess anything up. Remember earlier when I said this?
Flashback.
I can't help but feel like I'm using up all my good luck early on and something is going to go wrong at the end.
End of flashback.
Well, I definitely did use up all my good luck. So basically what happened, I had all the electronics mounted inside the enclosure and I had wired up all the sensor cables. I plugged in the Teensy, plugged it up to my computer, plugged the cables up to the robot, and I powered everything on, and all of a sudden I got a cloud of magic smoke out of the Teensy near the USB port. So of course I immediately turned off the power switch on the enclosure and started double checking everything to see what went wrong. Apparently I blew out a fuse on the Teensy. I believe it's a 500 milliamp fuse. At least that's what it says on the schematic. At first glance, I think I might have been drawing way too much current from the USB port than the Teensy can handle. But considering I tested this iteration of the board before putting everything into the enclosure, and I also used the previous iteration fine without any issues and I really didn't change anything, that leads me to believe somewhere in between testing the new control board and mounting everything inside this box, I made a mistake. Either I shorted the 3.3 volt and ground pin somewhere, or maybe one of the cables or connectors are faulty. Needless to say, that leaves a long list of things that could have gone wrong and gives me no good ground to basically start troubleshooting. So what I want to try first is testing all the connections and make sure everything is wired as I intended. Once I confirm that, I can then go ahead and double check all the connections on the control board and inside the panel, making sure I didn't accidentally short something out with like a blob of solder. Something went wrong and I basically just have to kind of rack my brain until I figure it out. But because I basically fried my Teensy, it doesn't really respond anymore, probably because it's not getting any power to the 3.3 volt regulator anymore. I had to pick up another one. And I also picked up a couple 3.3 volt regulators. So hopefully these can supply enough power to the I2C devices so that I don't have to use the Teensy, and hopefully can avoid that issue altogether. This is also the reason why this video is much later than I originally intended it to be, because now I have to spend time troubleshooting at what would have been the very end of the video. So, fun. But yeah, let's start troubleshooting. I spent many hours over the course of a couple days trying to pinpoint the exact cause of the Teensy burning out. The first step in my troubleshooting was to verify all of the connections on both the control board and GX16 connectors on the robot platform and the enclosure. Everything was wired up correctly, so this only added to my confusion. And as I stated before, the robot worked before I moved things into the enclosure. The only thing that kinda made any sense and could explain what happened was that the I2C sensors were drawing too much current from the Teensy and blew the fuse. Or perhaps I shorted power to ground briefly somehow during that test. Regardless, I decided it was best to use an external 3.3 volt supply and give the Teensy a break from powering things. I picked up this 3.3 volt buck converter from Adafruit to handle that instead. After installing the buck converter and desoldering the 3.3 volt headers on the Teensy, I fired everything up, and it worked. Alright, just a quick update video from my phone. No magic smoke for the Teensy. We have all 4 sensor wires enabled, or plugged in rather, and we're getting all of the values for the sensors coming through. Some of them are a bit off, and I think I may have crossed a wire or two for the I2C and mixed them up, but other than that, everything seems to be working fine, which is a huge relief off my shoulders, because now I don't have to worry about magic smoke for my Teensy. And I'm assuming this circuitry for the motors is still going to work pretty much as it was before, but I'll wire those up next and test those. Those are a bit simpler, they're only 4 wires each. But yeah, really good news, really good progress. Glad I got the issue sorted, whatever it was. So apparently, it was the USB-B to micro USB adapter I purchased that seemed to have caused the issue. I couldn't get it to work with any other USB devices during testing, so it was probably faulty to begin with.
I'm tired of this, Grandpa!
That's too damn bad!
Now that I know the sensors are working, I finished wiring the rest of the connectors up to the stepper motor drivers, double-checked the wiring one more time, and powered everything up for a final test. Alright, so we have everything wired up. All the connector inputs are connected to the robot. So let's go ahead and turn it on. And I'll go ahead, enable stepper motors are now locked into place, as you can see. Upload the sketch to the Teensy. Something seems to be broken. And I don't really know what. There's power going to this, but the Teensy isn't running the sketch properly. And I can't tell why. Well, guess we're doing some live debugging here. Alright, let me level with you real quick. There's about 40 to 60 minutes of footage that's just me rambling to myself trying to figure out what the issue is. Spoiler, it's a noise issue with the I2C sensors again. So I'm just going to skip to the end for you, okay? Okay.
2 hours later.
Two, three, go to 0. Oh, look at the jitter. Oh boy, the jitter. Oh, that's even worse. Why is it not? You think that's 0 now? Curious, if I move 50, will you go to? Yep, so I added it the wrong direction. Go figure. Yeah, so not quite sure how to get this working without the encoders, so I guess that's it for this video. I'll just have to sleep on it and figure out a solution to the noise problem, so we can hopefully get all the sensor data to the control box noise free. Yeah. Even though I was unable to get the sensors working with the stepper motors, I feel very happy with the work I got done in this video. Mechanically, the robot is very rigid, and it doesn't seem to miss steps when moving anymore. And despite the sensor issues, I'm really loving the cleaner setup for the electronics. It makes things easier to break apart and put away, which may come in handy if I decide to take this thing to any maker fairs. I've had this issue with the I2C sensors before, and since then, I've had this solution in the back of my mind for how I can fix that permanently. Unfortunately, that's going to take a bit more time to test and implement, but I'm fairly confident that once I do, it'll fix any issues I have with these sensors and any others I decide to add to the robot later on. If you're a fan of my content and you want to see more exciting projects like this one, you should consider supporting me through Patreon. As a Patreon member, you can get access to behind-the-scenes posts about this project and others, and depending on the tier you choose, you can also receive shoutouts in my videos or your name in the end credits of my videos. To support, you can visit patreon.com/StewartTechnologies. You can also find that link in the description down below. If you enjoyed this video, share it with a friend, and be sure to like, subscribe, and click the bell to receive a notification when the next video drops. Thanks for watching. Shout out to new Patreon members Elizabeth and G. Watts. Thank you for your support.